Good afternoon. My name is Fahad Pervaiz. I am a PhD student in the Civil Engineering Department doing research under Dr. Michel Hummel's supervision. My research is based on numerical simulation of hydrodynamic forces on the riverine and coastal bridges subjected to extreme weather events. The overall objective of the study is to establish validated computational practice to address the research needs of the transportation community in bridge hydraulics via computational fluid dynamics simulations. According to the IPCC, the temperature of the Earth is increasing due to greenhouse gas emissions and human activities. This change in climate is intensifying the water cycle, which brings more intense rainfall. On the other hand, rapid urbanization leads to less infiltration and storage of water in natural areas. Climate change, along with urbanization, causes severe flooding and changes the flood frequencies. According to the previous studies, floods and scoring are the reason of more than 50% of all bridge failures here in the US. If I talk about the bridge deck failure mechanism due to hydraulic loading, when water hits the bridge with a certain velocity, it exerts the drag force, which acts parallel to flow and affects the bridge deck's horizontal stability and can cause sliding of the bridge in the flow direction. On the other hand, lift and buoyancy forces that act perpendicular to flow can uplift the bridge deck. In addition, overturning moments around the center of gravity of the bridge can also occur due to uneven distribution of forces on the bridges. This research is valuable in a way that, in the past, bridge analysts and designers have relied on expensive scaled experiments to provide estimates of the flow field and structural response. But with the rapid development of supercomputing technology, commercial CFD code can provide an economic way to study these systems. Experimental setup. For the experimental setup, at first, the hydraulic parameters like water surface elevation, flow depth, channel velocity, fluid number, and bridge elevation of 43 creeks and about 900 stream crossing bridges in Harris and Travis County were collected from the hydraulic models obtained from the Harris and Travis County flood control districts. After the identification of flow parameters, we performed CFD modeling of the bridge decks. The numerical modeling was conducted using ANSYS Fluent CFD software. Flow parameters obtained from the hydraulic models were used in defining the boundary conditions in the ANSYS Fluent modeling. The performance of both scaled and full-scale bridge models with I-girder, box beam, and slab beam structure was examined under different flow conditions. Furthermore, we considered flat plate and wedge-shaped debris to evaluate their impact on the force coefficients. We also considered 15, 30, and 45 degree skewness to check its impact on forces. After choosing the proper mesh size, the boundary condition in the numerical domain were defined. The simulations were completed using the volume of fluid multiphase model and K omega SST turbulence model. This animation shows the flow of the water in the computational domain. After obtaining solution convergence, results were post-processed and analyzed. The numerical modeling results for different flow conditions were compared with the physical modeling results conducted by Dr. Ahmeri's research group here at UTA. On the left side, the top figure shows the flow lines obtained from the lab experiments by Dr. Ahmeri's group, and the bottom figure shows the results from the numerical model. It can be observed from the graphs and flow patterns around the bridge that the CFD modeling results show reasonable agreement with the physical modeling results. In the graphs to the right side, black triangles represent the results from physical modeling and other colors represent the numerical modeling results by using different turbulence models. The numerical model shows reasonable agreement except drag coefficient at higher indentation ratios. The main reason for the lack of agreement at higher indentation ratio could be the numerical modeling assumptions. Experimental results. The first row of graphs show the dependence of force coefficient on fluid number and indentation ratio. CFD model showed the dependence of the drag and lift coefficient on fluid number across the range of indentation ratio tested. In general, a higher fluid number decreases the drag coefficients and at higher indentation ratio and increases the lift and moment coefficients. The second row of the graph shows the dependence of the force coefficient on deck skewness. It can be observed from the graph that as the angle of deck skewness increases, the magnitude of drag and lift coefficient decreases. The third row represents the graphs which shows the dependence of force coefficient on the debris shape. The accumulation of flat plate debris increases the drag and lift coefficients, while wedge-shaped debris increases moment coefficient as compared to the no debris scenario. The fourth row of the graphs show impact of waves. Wave forces increases with the increase in wave height, and the vertical component of wave force has a much larger magnitude than the horizontal component. Overall, the CFD modeling results are used to inform the structure analysis of bridges to determine the design of countermeasures. And the CFD modeling approach allows for the flexibility in simulating a variety of flow and indentation scenarios, thus providing an important complement to the physical modeling. At the end, I would like to thank TXTORT for providing funding of the project through RTI 07068. I would also like to thank Dr. Ahmadi's research group for providing the physical modeling results and Bhupindra Rajacharya for providing bridge drawings. Thank you so much.